So, let us start this lecture with a thought process from great scientist Albert Einstein, who says, no, this trick won't work. How on the earth are you ever going to explain in terms of chemistry and physics so important a biological phenomena as first law? You know, first law is very important, and like, you know, very memorable for all of you and all of us rather. So, I mean, it cannot be explained through chemistry and physics, what Albert Einstein is talking about. But let us recall what we learned in the last lecture. We are basically looking at types of, you know, elementary reactions, chain branching, chain initiating, chain carrying, chain terminating. Then we use those, you know, chain branching reactions to explain how this chemical explosion will be occurring, right? And today what we will do, we will basically look at multi-step chemistry, and later on I will be dealing with how to minimize the number of chemical steps in the multi-step chemistry such that it can be tractable, right. So, let us look at a multi-step chemistry reaction for methane, which is a very simple, you know, hydrocarbons, right. And if you look at the methane molecule will be reacting with, let us say there is a radical, you know, of course, and then what will happen? CS3 plus S2, and this is what kind of reaction? This is basically chain carrying, because CS3 is a radical and H is a radical, right. So, the ratio is 1. This is a chain carrying reaction, yes or no, right. And similarly you can say that radical pull is there, so that CH4 is you know, reacting with O going to the CS3 and OH. In this case what will be? Chain branching, right. And CH4 plus OH getting into CS3 and water. What is this? This is basically chain what? Carrying, isn't it? Only one radical in the product and this thing and the reactant 1. So, if you look at, let us say CH4 is reacting with H, O, OH, any one of them, you know, that means 3 reactions I have given. It can go to CS3 and other things, these 3 reactions, you know, that is the indication. And then also it can go backward direction. This is forward if I say KF, and this is backward direction. CS3 can be combined with S2, you know, or H and something else and get into that, right. And CS3 will be, you know, reacting with CS3 get into C2H6, right. And C2H6 can be converted into C2H5, and C2H5 can be converted into C2H4. It can be getting into C2H3, you know, reacting with the what you call H and OH. It can go get into the C2H2, it can get into CS2, and then from this reacting with it get to the product oxygen. This is a, you know, some route. And there is another CS3 can be converted into CS2O, and then CS2 can be reacting with HOH getting into CHO and CO, right, and then CO will be reacting with OH getting into CO2. Similarly, there will be several reaction will be taking place here that way in this direction, and then there several product will be formed. C2H3 can come into C2H2 plus OH reacting with these products, and similarly from here it can CS3. So, what I am trying to show you in this multi-step reaction mechanism, you know, anything and everything can occur. It is not that this is the thing what is occurring in nature, okay. This is the model what people have devised. What exactly is happening? God only knows, or maybe in future some of you will do and say, look, this is the model I am proposing, right, better model. So, Are you getting? It is so complicated. But what I am going to show you, and this will be containing something maybe around 28 species kind of things, and then maybe more, and maybe something 200 odd reaction or more. But I will not be discussing that. It will, it will be very difficult. You can't observe also. If you want to look at, then you can look at Chemistry of Combustion. One book is there by Gardiner. It's a one book, Chemistry of Combustion. Okay. Then you can look at that chemistry about that. So what I will show you kinetics data for methane air system, which I had used a long time back, 20 years back, okay, for my PhD thesis. So I am just showing here. This contains something 14 species and 40 reactions. These are all 40 reactions, and keep in mind that here only C1 chemistry, that means C2H6, C2 like H5, H3 are not there, right. And this is for the forward reaction. You can get the backward reaction, all these coefficients, this is your active pre-exponential factor A, and this is the M coefficient. Here values are given, E is the activation energy, right. And you can calculate the reverse reaction rate by using what? This reaction rate you can calculate. This is Kf and this is Kb. You can calculate it using the equilibrium. At what the way we did, you can calculate, right, and then use that one. And this is giving fairly well about prediction of burning velocities and ignition delay and other things. Okay, and this simple one, and this can be computed even in your personal, computers like. So now, if you look at, as I told, people are using very long what you call number of reactions being used in chemical reactions for methane air and other higher hydrocarbon, because of course nowadays CNG being used, which contains methane, but it contains some other higher hydrocarbons also. But higher hydrocarbon means more number of species involved, more number of reactions, and it will take a lot of time to compute, right. And unless you are having a parallel computing, and if you are doing a very complicated problem like a internal combustion engine or gas turbine engine or rocket engines, like it will be hell of affairs to predict something meaningful using kinetics. Okay. So therefore, there is a need to reduce this mechanism and coming to the global kinetics, or maybe 2-step chemistry, 3-step chemistry, or maybe 5-step chemistry. There are various models are there. So for that we will be discussing two methodology only. There are several other also. One is quasi-steady-state approximation method model. In this case, what is being assumed, that you assume it has reached a steady state, and in this case we know that radicals form during combustion, right, and radicals life, half life is very, very small as compared to stable species. Okay. So therefore, I can say the rate of radical formation is equal to rate of radical destruction. I can say that, because in the certain time during that thing it will be there, after that it won't be there, right. It's like your if you look at the time scale of our let us say Indus Valley civilization, and ours is like a radical, we will be here doing something, contributing, and then go away. After that we won't be there. Similarly, radicals, is the role is that. So therefore, we can say the rate of radical formation is equal to rate of radical destruction. For that reason, we need to relate the radical concentration with measurable concentration of other species. Why we are saying? Because radical you cannot measure. It's very difficult to measure radicals. Okay. Of course, people are devising very sophisticated instruments. Still, it will be difficult, right? Because this will be in the order of femtoseconds, not microsecond, nano, femto, right? That kind of seconds. It will vary. So therefore, we can make this assumption. And we want to basic idea of this analysis also to relate this concentration of radicals in terms of stable species concentration, which you can measure. So how to relate this radical concentration with that of the stable species is the question what will be using addressing by using this approximation. So, for that we will have to invoke quasi steady state approximation. Let us consider that A is converted into A2 with the reaction rate of K1, and this I can say reaction 1, and then A2 is converted into to A3 is a 2 reaction. So, if you look at this is basically a series reaction, is not it? A1 is getting into A2, then A2 is getting into A3. Now, reaction rate of these 3 species, right, if you look at dCA 1 by dt is nothing but minus K1 CA1, right, and dCA 2 by dt is nothing but K1 CA1 minus K2 CA2, right, because this is coming from reaction 1, this one from reaction 1, this is from reaction 2, and dCA3 is from basically from reaction 1, that is K2 CA2, right. So, if I say this is basically what you call, this is 3 and this is your 4 and this is your 5, right, equation, I will have to solve this thing and relate and do some approximation by doing that, right. So, what will be the initial condition? Initial condition at time t CA will be C initial and CA2 will be 0, CA3 will be 0, yes or no? This will be 0, there will be no CA2, right, concentration will be 0 of A2 molecule and concentration of A3 will be 0. This is the initial condition which we will be using, right. Now, I will take this equation 3, right, and try to integrate, right. So, by integrating equation 3, we can get basically dCA 1 dt K1 dt. I can write down this is ln CA1 is equal to minus K1 T plus C1. And what will be C1? I will have to apply the boundary initial condition, right, at T is equal to 0, at T is equal to 0, CA1 will be CA in, is not it, yes or no? So, that means at T is equal to 0, this will be 0, and then what will be C1? C1 will be basically ln CA1 in. So, then I can write down, from this I can write down CA1 is equal to CA1 in e power to K1 T. If I take this is 6, right, this will be 7. And what we will do, we will use this using equation 7 in equation 4, right, equation 4, we will get dCA2 by dt is K1 CAI in 1, okay, this is A1 e power to the minus K1 T minus K2 CA2, right. This we want to solve, right. If you look at this equation, right, is which form? This is a differential, this is a ordinary differential equation of first order, right, and this is which form? Are you not getting? Okay, let me write down here, you will catch it very easily, right, is plus K2 Ca2, right, is equal to K1 Cai in Ek1T. This is which form? That is, if you look at dy by dx plus px y is equal to qx form, right. This is the first order ODE inhomogeneous, right. So, now I want to solve, I know the solution. What is that solution? We will have to find out basically integrating factor, right. In this case, what will be integrating factor? Integrating factor, right, what it would be? It will be E K2 dt, because this is your Px, right, this is your y. So, that is equal to E K2T, right. So, then what will happen? I will get this solution. The solution, this is okay, let me write down, this is 8, this is 8, okay, 8. The solution for equation 8, okay, what it would be? It will be Ca2E K2T is equal to, right, E K2T K1 Ca1 in, this is the term I am writing now, Qx, right, E power 3 K1T dt, right, isn't it? So, now I will not do that, you will have to do this thing by applying this initial condition, right, by applying initial condition that already we have discussed. This is your initial condition, right, right. So, I can get a solution like this, right. If I say this is 9, right, equation 9 becomes Ca2 is equal to Ca in K1 by K2 minus K1 T minus K2T, right. This is your equation, okay. Now, we will have to basically look at now expression for the Ca3, right, and we will, what we will do, we will have to use this thing, see equation 10 here. Why? Because if you recall that equation 4, right, is expressed in terms of Ca2, right, because we know Ca3, right, we know that dCa3 by dt is nothing but K2 Ca2. So, by using equation 10, we can get, this is equation 5, equation 5 becomes dCa3 by dt is equal to K2 Cai in K1 K2 minus K1 E minus K1T minus K2T, right. And I will have to integrate this equation, like this is, let us say 11, by integrating equation 11 and using initial condition, right, we can get, I am omitting some steps, okay, we can get Ca3 is equal to Ca in K1E K2T divided by K1 minus K2 plus K2E minus K1T divided by K1 minus K2. This you will get this expression, right. So, you can get, and using initial condition here, T is equal to 0, Ca is equal to Ca initial, 1 initial, and Ca2 is 0 and Ca3 is 0, right. So, you will have to apply that and you will get this. Let us now look at, you can get this thing expression what I have shown. Now, what we will do, this is the analytical form, right, you are getting, and analytical form, if I just do that thing with respect to time, you will get this is A1 is decreasing, right, and A3 is increasing, that is obvious thing, right, and A2 is, there is a little peak here and then after that remaining same. With this, these are analytical tools, right. But let us say it is a very simple one, we are getting analytically, but in the complex one we won't be, we will be doing some approximation, that is quasi steady state approximation, right. And if I look at what I am doing, by applying this method, we are saying that Ca2 intermediate, that space is Ca2, which will be not remaining, I am saying it is 0, it is remaining 0 kind of things, like the change in 0. So, therefore, K1 Ca1 is equal to K2 Ca2, right. Then I can write down as, it is a very simple one, right. And so, therefore, earlier it was basically Ca3 is equal to K2 Ca2, right, is equal to K2 Ca2, and then I am saying this is K1 Ca1, right. Are you getting? Okay. So, Ca3 is, if you look at Ca1, right, in place of Ca1, I have already got this result from the beginning, right, and then I can get this one. So, by integrating above this equation, right, we can get that this is basically Ca3 is equal to Ca1 in 1 minus K1T, and this is very easy, you can do that, right. So, now I got these values, Ca3 in terms of Ca1 and Ca2, right, and then I can plot these values. This will be possible only when K2 is greater than K1. K2 is very fast reaction as compared to the K1. Otherwise, you cannot apply this kind of approximation. If you do that, what you will get? You will get basically the similar values for the Ca1, right, concentration, and keep in mind this is concentration of Is species with respect to initial species, right, of A1 and with respect, but and also you will get similar prediction for the A3, there is no problem, but problem is here, right, it is having some finite value at 0, which is not true, right, because in the beginning it was supposed to be like that 0, right, I have shown, but it is not true, that means this is violating, it is not possible to have that, but however later on it is same. So, if I am considering in this region, then it will be fine, it is predicting well. So, therefore, this is the limitation of this approximation method, but however we can simplify the reactions and we can also express in terms of that. Let us look at the partial equilibrium approximation, right. There is a quasi steady state, that means something is attaining the steady state, but here we are saying partial equilibrium approximation. And why it is required? Because the reaction, certain reaction will be having faster rate, certain reaction will be slower rate, and if it is faster rate, then we can say it is quickly attaining the equilibrium. Are you getting? It is quickly attaining because it is very fast. So, therefore, we call it as a quasi equilibrium state or partial equilibrium like kind of thing. The partial equilibrium expresses concentration of unknown species in terms of known concentration. So, how is PA is carried out? Let us consider NO formation mechanism, like O is reacting N2 is getting into NO plus N, right. And let us say this Kf value is given to you, right, this some coefficients is known to you, and reaction rate of NO species I can write down dCNO divided by dt is equal to Kf CO N2. Keep in mind that CO is a radical, the concentration of O is difficult to measure, right, this is the radical, right, and N2 is a stable species, so you can very easily measure, right. And however, you need both concentration of O and N2 to determine the reaction rate of the NO. Now, how to go about it? And what we can say, the rate of formation and destruction of O is very high, that is the assumption, right, because it is very fast, so will be. And with this as a result, of course, it is very difficult to measure the concentration of O, that I have already. Now, how we will handle it? Basically, what we will have to do, we will have to invoke the equilibrium, okay. And step 1, assume the partial equilibrium O2 molecules, right. That means I will consider that and then try to relate O2 with the molecule with the O, right, and I will consider O2 is getting into 2O and then it has attained equilibrium, right. From that I will find out equilibrium constant Kc is equal to CO, concentration of O2 half, right. If I know this Kc at certain temperature, of course, right, then I can very easily substitute this CO by concentration of O2 and then I will get CO is nothing but Kc, concentration of O2 power to the half and reaction rate of species became Kf Kc, concentration of O2 half into 0.5 CN, right. This is basically the reaction rate NO is a function of concentration of O2 and Cn2, of course Kc is there and Kf is there, but concentration wise the Cn2 will be playing a major role, not the oxygen, right. So, what is the difference between PA and quasi-static state approximation? PA is the partial equilibrium approximation, right. Reaction attains a steady state, that means this reaction attaining a steady state, but in this case species attain the steady state, there is a difference, are you getting? And as I told, this is the part of this reaction, whatever example we have considered is a thermal NO, though thermal NO or the NO formation due to temperature is less dependent on concentration of O2 because this is power half. So, therefore, it is less dependent and it is dependent on the temperature, therefore, we call it as a thermal NO, and NO reduction by reducing the combustion temperature you can get, you can reduce the NO formation due to, of course, the thermal mechanism by reducing the temperature. So, keep in mind that in real situation particular reaction may not attain equilibrium, okay. Therefore, you will have to apply it cautiously, and PA partial equilibrium provides satisfied result only at the high temperature, it will not give you good approximation at the low temperature. For example, we will consider that, let us say that I am having a C3H8 air flame at 0.1 megapascal and 298, and then I am plotting what you call concentration profiles, right, these are concentration of species versus the what you call flame, flame means across the flame, if there is a flame here, let us say, right, I am going by the Z direction, this is my flame, okay, one dimensional flame and this is Z direction, I am plotting Z. Now what will happen, of course this is your temperature, right, this side is, the scale is temperature, and this is your propane. Propane is given, so therefore my like kind of things. And what will happen to the O, right? If I say detailed mechanism, this is a solid line, but if I take partial equilibrium mechanism, O will be like this. That means, and if I take only equilibrium, which you have done, this is the data is here, is remaining constant, it is not changing. Are you getting? So therefore at this equilibrium, at the high temperature zone, because if you look at, if I am saying this is your Z, this is 0, my flame is here somewhere nearby, so therefore the temperature here will be higher, and this temperature will be very low in this region, right, because this is the temperature, na? In this region temperature is very high. So at the high temperature, these both are partial equilibrium, detailed mechanism is approximately same or almost same, and this is possible only on the high temperature. But if I consider here in this region, it will be diametrical, it is not wrong, it is not right, because here temperature is not that high as compared to this, and if I consider here in somewhere where lower temperature is there, so it will be quite different. So therefore partial equilibrium method has to be applied at the high temperature only. Okay. Global kinetics, why you will go for global kinetics, why not multi-step chemistry? Because there are several reaction mechanisms we would like to involve, we would like to consider to get a predictions, and if we will do that, the computationally it will be very difficult and analytically impossible. You cannot have anything analytical means you could write equation and do that, impossible. Even computationally it will be very what you call costly. So therefore we always go for a global kinetics, particularly if the flow problem is complex or the engineering problem like your IC engine, gas turbine engine, other thing. Therefore there is a need to go for global kinetics. What is that? That is basically single step combustion, you can say. People are talking about what you call reduced mechanism, 2 steps or 3 steps, but I will consider as a single step as a global kinetics. Let us say methane, 1 mole of methane reacting with 2 moles of oxygen getting into carbon dioxide and 2 moles of water, right. And whether the reaction occur in nature, certainly no, it is just a model, right. And overall reaction I can write down CH4 dt is equal to A E exponential factor of like this is exponential activation energy, this is your activation energy, right. And RU is a universal gas constant, T is temperature, and this is the concentration of methane and oxygen, and these are coefficients, that has to be obtained, and this generally obtained by matching the heat release profile, right. And this A values is the pre-exponential factors, right, and which has to be obtained, the some values. So and you can get a kinetic scheme for arbitrary hydrocarbons, right, and this is the things you can it is a similar, I can instead of methane I am just writing CXHYMN, right. Are you getting? This is just a generalizing. Now I can get this in terms of a tabular data, and then or the data will be there in the table and you can use that, or you can conduct experiment and do. Keep in mind that this data what I am going to show you is basically for various fuel, and this is the pre-exponential factor AF or A, whatever you call, is the same as A what I am using, and activation temperature basically E by RU is nothing but your activation temperature, right, and this given, and M is our coefficients, right. Keep in mind that these values will be varying from various resources, like, or various sources rather. It is not that it will be same, that is why I was telling this A values will be quite different, and then so also activation energy. Here he has taken all activity same, need not to be, this from the just a kind of things people have done modeling and then use it, it need not to be same, okay. Are you getting my point? This number will be very different from various sources if you use. So, generally we use this thing, and I will stop over with this, and in the next lecture we will be discussing about physics of the combustion part. Thank you very much.